The James Webb Space Telescope was built to look deeper into the universe than humanity had ever managed before. Far beyond the orbit of Earth, protected by its enormous sunshield, Webb studies light that has traveled across billions of years. Every photon carries information from the distant past. And when astronomers analyze that ancient light, they are effectively looking into a universe that existed long before Earth, the Sun, and even our solar system. One of the most remarkable observations involved an extremely distant galaxy, one that existed only a few 100 million years after the universe began. At first glance, scientists might have expected to find a primitive collection of young stars. Instead, the galaxy appeared surprisingly developed. Its compact region contained an enormous amount of material, while huge numbers of young stars were producing intense amounts of radiation. But the brightness was not the most interesting part. The real surprise appeared when researchers separated the galaxy's light into its individual wavelengths. Hidden inside that spectrum were chemical fingerprints. Among them was evidence of oxygen. That may sound ordinary because oxygen is everywhere on Earth. But in the early universe, oxygen should have been far less common. Immediately after the Big Bang, the cosmos consisted mostly of the lightest elements, especially hydrogen and helium. Elements such as oxygen, carbon, and nitrogen had to be produced later. Stars became the factories that created these heavier elements. Massive stars formed, burned through their fuel, and eventually ended their lives in violent explosions. Those explosions scattered newly created elements into surrounding space. The enriched material could then become part of another generation of stars and planets. So finding oxygen in such an ancient galaxy suggests that this chemical evolution had already progressed significantly. In other words, stars may have formed, evolved, and enriched their surroundings much faster than early models once assumed. Perhaps the young universe was not a quiet place slowly building itself piece by piece. Maybe it was already experiencing intense bursts of star formation. Massive stars could have appeared quickly, lived short but extremely powerful lives, and then exploded. Their remains would have seeded the surrounding environment with heavier elements. Those materials could then have become the ingredients for new stars, planetary systems, and eventually the chemistry necessary for life. The discovery therefore provides more than a picture of an ancient galaxy. It gives scientists a glimpse into one of the earliest stages of cosmic chemical evolution. But Webb's investigation did not stop at the distant universe. The telescope also studies objects much closer to home, including some of the strangest bodies known to astronomy. One such object is a brown dwarf. Brown dwarfs exist somewhere between planets and stars. They can be considerably larger than planets, but they do not possess enough mass to sustain the kind of long-term nuclear fusion that powers ordinary stars. Because of this, they are sometimes described as failed stars. But that description can make them sound far simpler than they actually are. Their atmospheres can contain complicated chemistry and dramatic weather. Webb has helped astronomers investigate molecules such as methane and water vapor within these unusual objects. The atmosphere of a brown dwarf can be turbulent, with clouds, temperature variations, and powerful atmospheric processes. And then there is another fascinating possibility. Some brown dwarfs display unusual glowing activity high above their atmospheres. These emissions can resemble auroras. On Earth, auroras occur when charged particles interact with magnetic fields in the upper atmosphere. Similar processes may be responsible for some of the strange emissions observed around brown dwarfs. Scientists have even considered whether an unseen companion could influence the object's magnetic environment. Perhaps a small orbiting body is producing gravitational or magnetic effects that are indirectly visible. The companion itself may remain undetected, but its influence could leave a measurable signature. This is one of the most powerful ideas in astronomy. Sometimes scientists cannot see an object directly. Instead, they discover it because of what it does to something they can observe. And Webb continues to search for exactly these hidden clues. The telescope's observations are showing that even objects that appear faint and isolated can contain complex environments. From galaxies existing near the beginning of cosmic history to strange objects that never became full stars, the universe continues to reveal structures that are more complicated than they first appear. And this is only the beginning of the story. After studying distant galaxies and mysterious brown dwarfs, the James Webb Space Telescope turns its attention toward another extraordinary part of the universe: planetary systems. Unlike our solar system, where most planets follow relatively predictable paths, other systems can be dramatically different. Some giant planets travel along highly elongated or tilted orbits. Instead of following nearly circular paths, these worlds may swing far away from their stars before returning again. Such unusual orbits can reveal a violent history. A planet may have been disturbed by another massive world. A companion star could have passed close enough to alter the system's architecture. Or powerful gravitational interactions during the system's early formation may have pushed planets onto unstable trajectories. The important point is that planetary systems are not necessarily born in the orderly arrangement we see around the Sun. Their histories can be chaotic. Worlds can migrate. Planets can collide. Some can be thrown completely out of their systems. And others can slowly spiral toward the very stars that created them. Webb has helped scientists investigate planets undergoing extreme conditions near their host stars. Imagine a giant gas planet orbiting so close to its star that enormous gravitational forces are constantly acting upon it. With every orbit, tidal forces can stretch the planet's atmosphere. The star's radiation can heat the outer layers to extraordinary temperatures. Over long periods, the planet may begin losing material. Gas can escape from its atmosphere and form enormous streams extending into space. Eventually, enough material could be removed to dramatically transform the planet. In the most extreme scenario, the world could ultimately be destroyed. This reveals something important about planetary evolution. Planets are not permanent structures. Their existence can depend on the balance between gravity, radiation, temperature, and orbital motion. Some survive for billions of years. Others may have much shorter cosmic lifetimes. And while one planet is being destroyed near its star, somewhere else another planetary system may be forming from a disk of gas and dust. These environments contain countless fragments of material. Over millions of years, particles collide and combine. Some grow into larger bodies. Those bodies can eventually become planets, moons, asteroids, and comets. Other collisions may destroy objects and create enormous fields of debris. The process is messy. It is unpredictable. But eventually, gravity can transform that chaos into organized planetary systems. When astronomers connect all of these observations, a much larger picture emerges. The universe is not static. It is constantly transforming. Stars are born inside clouds of gas. They shine for millions or billions of years. Eventually, many of them die and return material to space. Galaxies interact and merge. Black holes grow. Planets form and sometimes disappear. Chemical elements are created inside stars and distributed across the cosmos. And some of those elements eventually become part of new planetary systems. That means the material around us has an extraordinary history. The oxygen we breathe, the carbon found in living organisms, and many of the heavier elements present on Earth were produced through ancient cosmic processes long before our planet existed. The universe built the ingredients first. Earth inherited them later. This is why observations from JWST are so important. The telescope is not simply collecting beautiful images. Its instruments are analyzing the chemical fingerprints, temperatures, structures, and motions of objects across enormous distances. Every spectrum is another piece of evidence. Every distant galaxy provides another chapter of cosmic history. And every unexpected observation gives scientists a reason to improve their models. Some discoveries may confirm ideas that have existed for decades. Others may force researchers to modify those theories. And occasionally, a future observation could reveal something that requires an entirely new explanation. That uncertainty is not a weakness of science. It is the reason exploration continues. The deeper Webb looks into space, the further humanity travels into the history of existence itself. We see galaxies that formed when the universe was young. We observe stars producing the elements required for planets. We investigate strange worlds being transformed by their stars. And we study environments where new planetary systems may still be taking shape. All of these observations tell the same story. The cosmos is dynamic. It is constantly creating, destroying, and rebuilding. And somehow, within this enormous cycle of violence and transformation, a small planet around an ordinary star became capable of asking questions about the universe that created it. The James Webb Space Telescope is helping us trace that story backward. Every ancient photon is another message from the past. And with every new observation, humanity gets a little closer to understanding how the universe became the extraordinary place we see today.